elevator and aileron 0. And then I do it the other way around. And then I do it negative. So it takes time to do action, one full action, right? So it's not sufficient to just look at the sensitivity. Here, what do you multiply? The point is, this goes actually to the thing that we will learn through the course called motion planning. How to move along the Lie bracket by this out of phase square waves or sinusoids. It doesn't have to be a square wave, it can be a sinusoid. So for the direct control action, we give full aileron. This is the maximum aileron that we can achieve, 30 degrees, just constant. So it's like the pilot giving full step, wheel to the right. And here, remember, we do interactions between elevator and aileron. We do it in the form of sine waves, not square waves. And here is the result. This is using the conventional, like 2 degrees over 1 second, roll for the airplane. This is like 8 degrees, roll for the airplane. It's like, 4 times enhancement. Yeah, we didn't have these results back then. I mean, actually, it's very recent. I will go to the last topic. Remember, I promised you 3 benefits. First is the global results, right? Not local. The second is nonlinear controllability, how to move along directions that we cannot move. And these results you can apply to wherever. You just pick a system. This is the point. Pick a system. Yes, Carlos?
Can we recover the conventional result at low angles of attack using the Libre method?
No, this is a very good question. Look at this. This is a very good question. Here at low angle of attack, right? The sensitivity, see, inbuilt error is very large. And the slope is 0, almost 0, right? Which makes sense. In the linear regime, small angle regime, the linear mechanism, this is the linear mechanism, is better, much better. And the nonlinear mechanism doesn't work. And in the nonlinear regime, near stall, the linear mechanism fails and the nonlinear mechanism behaves much better, right? What I'm trying to say here about these Lie brackets, pick any system, whether it's network dynamic system, whether it's a combustion system, whether you name it. Pick any system and ask the following questions. Will I maintain my controllability if one actuator fails, if one of my inputs fail? What more will I get if I do Lie brackets between my inputs? Because I can assure you that in your field, nobody has looked on Lie brackets. So if you did, you will get more interesting results, okay? And the application is super simple. Just do Lie brackets, and Lie brackets are differentiation. Actually, most of the work will go through how to formulate the problem in this form. F plus G1 plus G2 and so on and so. But then the application will be very easy. So this is pretty generic. You can just apply it to whatever. This part, we didn't have a chance to go through last year. I mean, not in the introduction lecture, but in the course. But this year we will rely on some lectures from 241 dynamics recorded, so we'll have some room for the vibrational stabilization. It's an interesting part, actually. So x dot equals ax, almost everybody in this room has seen this and very, very familiar with this equation. And we all know that if all the eigenvalues of A lie in the left half plane, the system is stable. It's exponentially stable. Globally, asymptotically, exponentially stable. But the point is, if A becomes time varying, you might think that if all the eigenvalues lie in the left half plane for all times, you might think that the system is stable then. And actually, the point is no. So if all the eigenvalues of this guy lie in the left half plane for all times, this does not guarantee stability. We have a counter example. These guys provided an example for an A matrix whose eigenvalues lie in the left half plane for all times, and the system is unstable. So time varying system, they are challenging. We will study them in detail. Hopefully, we'll have a look on Floquet theorem, and we'll see what the geometric control can tell us about. So when we have a time periodic system, for example, so A of t is periodic, cosines and sines. Like I said, this is challenging to study its stability and so on, so because eigenvalues are not sufficient condition. Geometric control theory combined with averaging, they will provide some tools, which we will study in this course. They will convert this time periodic system into a time invariant system. There's no time anymore. And we are very familiar to study time invariant system. I will linearize and check the eigenvalues, and I'm done. So here is an example, like a pizza pendulum. So it's an inverted pendulum, okay? And the pivot is subject to vertical oscillations, okay? Write down the equations of motion, pretty simple. Theta double dot G over L sine theta reminiscent of the pendulum dynamics. Some damping if you like. And we have here the effect of this acceleration up and down, okay? So here is in a clearer form. Let's substitute our Z, the up and down, by a periodic function, Z cosine omega t. Let's substitute here and get this result. So it's a time varying system. Let's put it in a state space form, please. So we have d by x dot equals a times x, and my a has omega t. It has time limits. As I said, you cannot check the eigenvalues, it will not give you anything. So one of the standard techniques is to, let's do averaging, because this is cosine omega t is something like doing that, and it's very fast. So it's as if the system is just, doesn't feel this high frequency oscillation, just feels the average of it. So let's average out. Unfortunately, if you average out, this is cosine, so the average of cosine is 0. So when you average out, we have over bar here means averaged quantity. So here is your x dot equals a times x. Your a now doesn't have time, so you can check the eigenvalues fine, okay? So let's check the eigenvalues here. Without going to check the eigenvalues, I know if my a in this form, this is the controllable form if you took 270a. Just check if these guys are negatives. If these guys are negatives, you're done. So look at this. So this is already negative because the mu is the damping coefficient positive. What is delta? Delta here is g over L. So it's not negative. Okay? Delta is your g over L. So to have stability for this system, I must have delta be negative. But delta is g over L, I cannot change it. So there is no stabilization. This analysis tells you that by doing oscillation for the inverted pendulum, you can never stabilize it. Whereas, let's do what geometric control will tell us. So this is my system. I will not just do averaging. I will do averaging with the aid of geometric control. So if you do that, you will get this result. So here is the result. Again, it's x dot equals a times x. A is time invariant. There is no time. Go and check eigenvalues. Because it's simple. I know that if these guys are negative, I'm done. This is negative. So all what I need to achieve is that delta is smaller than this guy. Delta is g over L, is the instability source due to gravity, g over L. And alpha is what? Alpha is the amplitude of cosine. This is how much you do your forcing, okay? So if this is smaller than your some forcing term, or your forcing term is larger enough, you get stability. And this is what we call vibrational stabilization. We have a system that is unstable, it's the inverted pendulum. You just vibrate it around, you get stability, okay? And if you look at this term, look at this term. So here is the system. When you average out, the cosine goes away, but we don't average out directly. We do it using geometric control. So when we do that, we get an extra terms, and if we try to interpret these extra terms, it reads as follows. d by dt for theta dot, this is theta double dot, equals this term times theta. So pitching, this is theta's, what's that? If you multiply here by I, right? I theta double dot, so this is the torque. A torque that is proportional to angle, and you have negative signs like torque is negative k theta. This is a spring action, right? This is like a spring. Here is the video that we showed every meeting in our group. Inverted pendulum. It's unstable, right? You vibrate it up and down, you get stability. The interesting point, here is the interesting point. Look at this behavior. It's indeed as if we have a torsional spring. It's almost exactly the same behavior as if we have a torsional spring and we see it. We see it from the equations. Here is your K, here is your torsional spring, equivalent torsional spring. And what we're claiming is that this is also happening for insects. When we analyze insect flight dynamics, this is the hawk moth at the hovering position. It's a slow motion video because insects move their wings much faster. And this is when we do, this is the dynamics is fourth order, not second order. This is when we do direct averaging, and this is when we do averaging with geometric control. Here is the extra term that was not there, and when you interpret it, it reads as follows. Theta of the insect, the pitching angle of the insect, again if you multiply by I, this is the torque, that is negative K theta, this is indeed the spring action. So we have also witnessed or observed the same phenomenon happening with insects. Here is our experimental setup. You can go to our lab and see it. And interestingly, again, 2 years ago, we were at this level. We didn't have experimental proof for what's going on with flying robots. Now we have it all the way. So here is our mechanism. This is 2 degrees of freedom. It can go up and down, but it also pitches up and down. You can see that it's crazy unstable because it's at low frequency. If we increase the frequency, now we have more lift. If you push it all the way, it doesn't matter. You can go to the lab and visit it and just push it all the way. Don't be afraid. It's very robustly stable. So we have proved recently that indeed insect flight enjoys vibrational stability.